You are listening to Asynchronous Power, the developer's guide to Amazon SQS. Like and subscribe to keep up to date on our latest audiobooks. Asynchronous Power, the developer's guide to Amazon SQS. 1. The world of asynchronous computing and why SQS matters. In the fast-paced world of digital services, users expect instantaneous responses. Applications must handle millions of requests, and systems need to be available 24/7. Achieving this level of performance and reliability often hinges on a concept known as asynchronous computing. If you've ever wondered how your favorite online store handles thousands of orders every second, or how a social media platform processes millions of likes and shares without slowing down, the answer often lies in the power of asynchronous operations, and specifically, message queuing services. At its heart, asynchronous computing means that when one part of a system requests an action from another, it doesn't wait around for the action to complete. Instead, it sends the request and then immediately goes back to doing other work. Think about ordering food at a busy restaurant. In a synchronous world, you'd place your order and the chef would only cook your dish, ignoring all other customers until it's ready. You'd then receive your food, and only then would the chef move on to the next order. This is highly inefficient. In an asynchronous restaurant, you place your order, the waiter, representing the initial service, notes it down and adds it to a queue in the kitchen, the cooking system. You then return to your table, perhaps chat with friends or browse your phone. The kitchen, meanwhile, processes orders from its queue, handling multiple dishes for multiple tables concurrently. When your order is ready, a different waiter, perhaps a notification service, brings it to you. The key is that the initial order placement didn't block you or the kitchen. The challenges of tightly coupled systems. Before the rise of asynchronous patterns, many applications were built as large, monolithic blocks of code. All components, user interface, business logic, database interactions, external service calls were often intertwined within a single application. While simpler to build initially, these tightly coupled systems faced significant challenges as they grew. Scalability nightmares. If one part of the application, say an email notification module, became a bottleneck during peak times, the entire application would slow down. Scaling meant deploying more copies of the entire monolith, even if only one small part was stressed. Fragile resilience. A failure in any single component could bring down the whole system. If the database connection dropped, the entire application might crash, impacting all users. Deployment and development bottlenecks. Making a small change to one part of the code required retesting and redeploying the entire monolithic application, leading to slower release cycles and increased risk. Developers often had to coordinate heavily, leading to reduced agility. Resource inefficiency. Components that were rarely used still consumed resources because they were bundled with the frequently used parts. Message queuing. The decoupling solution. To overcome these challenges, software architects began embracing distributed systems and microservices architectures. In these designs, applications are broken down into smaller, independent services that communicate with each other. But how do these services talk without becoming tightly intertwined themselves? This is where message queuing services come in. A message queue acts as an intermediary, a durable buffer, between different parts of a system. Instead of directly calling another service, one service, the producer, sends a message to a queue. Another service, the consumer, then retrieves messages from that queue and processes them. This simple concept delivers profound benefits. Decoupling. Producers don't need to know anything about consumers, and vice versa. They just need to know the queue. This makes services independent, allowing them to evolve, scale, and fail without affecting each other. Load balancing and spikiness handling. If a sudden surge of requests comes in, the queue buffers them. Consumers can process messages at their own pace, preventing the system from being overwhelmed. More consumers can be added to handle higher loads, and fewer can run during quiet periods. This is exceptionally efficient for handling bursty traffic. Enhanced reliability. If a consumer service goes down, messages remain safely in the queue until the service recovers. No data is lost. This is known as message durability. Asynchronous processing. Long-running tasks can be offloaded to a queue, allowing the requesting service to respond immediately and continue with other work. For example, a user signing up for a service gets an instant welcome message, while the backend processes welcome emails, profile initialization, and analytics updates in the background via a queue. What is Amazon SQS? Your go-to-message queue. Among the many message queuing services available, Amazon's Simple Queue Service, SQS, stands out as a pioneering and foundational cloud offering. Launched in 2004, it was one of the very first services offered by Amazon Web Services, AWS, demonstrating Amazon's early understanding of the critical need for scalable, distributed messaging. SQS is a fully managed message queuing service. What does fully managed mean for you, the developer? It means you don't have to worry about provisioning servers, installing software, patching operating systems, or managing network infrastructure. Oz handles all of that complexity. You simply create a queue, send messages to it, and receive messages from it. This dramatically reduces operational overhead and allows you to focus on building features, not managing infrastructure. The simple in SQS reflects its design philosophy. It aims to be easy to use and integrates seamlessly with other AWS services. Its core value proposition is enabling reliable, scalable, and highly available communication between distributed software components, specifically by acting as that crucial buffer. Key benefits of SQS for developers. Effortless scalability. SQS is designed to scale elastically. Whether you're sending a few messages per minute or millions per second, SQS automatically adjusts its capacity to handle the load without any manual intervention from you. High availability and durability. Messages are stored redundantly across multiple availability zones, geographically distinct data centers, within an AWS region. This means your messages are highly durable and available even in the event of a localized outage. Reduced operational burden. As a serverless service, there are no servers to manage. Oz takes care of patching, backups, and underlying infrastructure, freeing up your team's time. Cost-effectiveness. SQS operates on a pay-as-you-go model. You only pay for the messages you send, receive, and store. There are no upfront costs or minimum fees, making it incredibly economical, especially for variable workloads. Built-in features. SQS offers features like message delays, customizable message retention, and dead letter queues for handling messages that can't be processed, simplifying the development of robust messaging patterns. Getting started. Setting up your AWS environment. To work with SQS, you'll need an Oz account. If you don't have one, setting it up is straightforward via the AWS website. Once you have an account, the primary tools for interacting with SQS as a developer are the AWS Management Console, a web-based interface that allows you to create, configure, and monitor SQS queues visually. It's excellent for exploration and initial setup. The AWS Command Line Interface, CLI, a powerful tool for managing AWS services from your terminal. It's perfect for scripting and automating tasks. AWS Software Development Kits, SDKs. These are libraries available for popular programming languages like Python, Java, Node.js, Net, Go, and many more that allow your application code to directly interact with SQS. For example, your application can use the SDK to send a message to a queue, receive messages, and delete them after processing. For the purpose of this book, we will describe API actions and concepts using a language-agnostic approach. While real-world applications use SDKs to call these actions, understanding the purpose and parameters of actions like send message, receive message, and delete message is crucial, regardless of the programming language you use. We will explain how these interactions work conceptually, focusing on the what and why rather than dwelling on line-by-line code examples, which are better suited for specific programming tutorials and would not translate well to an audio format. Before diving into the specifics of SQS, ensure your Oz account has the necessary permissions. You'll typically need to grant an IAM, Identity and Access Management, user or role permissions to create queues, send messages, SQS, send message, receive messages, SQS receive message, and delete messages, SQS delete message. These granular permissions ensure your applications have only the access they need, adhering to the principle of least privilege. In the following chapters, we will unravel the intricacies of SQS, starting with its fundamental building blocks and progressing to advanced patterns, security considerations, and best practices. By the end of this book, you will have a comprehensive understanding of how to leverage Amazon SQS to build highly scalable, resilient, and decoupled applications. 2. SQS Fundamentals. Understanding the building blocks. To effectively wield the power of Amazon SQS, we must first understand its fundamental components and how they interact. SQS, at its core, is deceptively simple, but the nuances of its message lifecycle, identifiers, and configuration settings are crucial for building robust and predictable systems. Imagine a sophisticated dispatch system. Messages are the packages, the queue is the sorting facility, producers are senders who drop off packages, and consumers are delivery drivers who pick them up. Let's break down these elements. Core components: queues, messages, producers, and consumers. Queue: this is the central storage mechanism for your messages. In SQS, a queue is a named entity that holds messages until they are retrieved and processed. Each queue has a unique URL that acts as its address. When you create an SQS queue, you are essentially setting up a dedicated channel for messages to flow through. Think of it as a specialized inbox for automated processes. Message. At its simplest, a message in SQS is a piece of data. It can be a simple text string, a JSON document, or any other textual information. Messages have a maximum size limit of 256 kilobytes. This size includes not only the message body, but also its message attributes, which we'll discuss next. For larger data, SQS is typically used to transmit references, like an S3 object key, rather than the data itself. Producer. The producer, also known as a sender, is any application or service that sends messages to an SQS queue. This could be a web server processing user requests, a data ingestion pipeline, or an automated monitoring script. Producers use the SQS API action send message to place messages onto a queue. Consumer. The consumer, also known as a receiver, is any application or service that retrieves and processes messages from an SQS queue. Consumers use the Receive Message API action to fetch messages. After processing a message successfully, the consumer is responsible for deleting it from the queue using the Delete Message API action. If a message isn't deleted, SQS will eventually make it visible again for another consumer to process, which is a critical aspect of SQS reliability model. The message lifecycle within SQS. Understanding how a message travels through SQS is key to designing resilient applications. The typical SQS message lifecycle involves several distinct stages. Sending a message. A producer, e.g., an AWS Lambda function, an EC2 instance, or an on-premises server, calls the Send Message API action, specifying the queue's URL and the message body. The message is then durably stored within SQS, replicated across multiple availability zones within the AWS region to ensure resilience. Message stored and waiting. Once sent, the message resides in the queue, waiting to be picked up by a consumer. During this period, it's considered visible and available for retrieval. Receiving a message. A consumer calls the Receive Message API action. SQS then returns one or more messages, up to 10 messages in a single request, by default, that are currently available in the queue. Message becomes invisible during processing. This is a crucial step. When a consumer successfully retrieves a message, SQS does not immediately remove it from the queue. Instead, SQS makes the message invisible to other consumers for a specified period called the visibility timeout. This prevents multiple consumers from processing the same message simultaneously, which could lead to duplicate work or data inconsistencies. Imagine a package being picked up by a delivery driver. While it's in their truck, it's not available for any other driver to pick up. Processing the message. The consumer now attempts to process the message. This could involve updating a database, calling an external API, performing calculations, or any other business logic. The consumer must complete its processing within the visibility timeout period. Deleting the message. If the consumer successfully processes the message, it must explicitly call the delete message API action. This action informs SQS that the message has been handled and can now be permanently removed from the queue. Each message received includes a unique receipt handle that must be provided when deleting it, ensuring that only the receiving consumer can delete that specific instance of the message. Timeout and potential redrive, if not deleted. If the consumer fails to process the message within the visibility timeout, e.g., due to an error, a crash, or simply taking too long, or if the consumer crashes before deleting the message, the visibility timeout expires. When this happens, SQS automatically makes the message visible again in the queue. This makes it available for another consumer, or the same consumer, if it has recovered, to retrieve and attempt to process again. This mechanism is critical for ensuring that messages are eventually processed, even if a consumer fails. Messages that repeatedly fail to process can be automatically sent to a dead letter queue, a topic we'll cover in Chapter 5. Message attributes, attaching metadata. Beyond the main message body, SQS allows you to include message attributes. These are structured metadata items, like key-value pairs, that can be attached to a message. They are distinct from the message body and are intended for metadata such as message type, routing information, timestamps, or application-specific identifiers. Purpose. Message attributes allow consumers to quickly inspect metadata about a message without having to parse the main message body. For instance, a consumer might look at an order type attribute to determine if a message should be handled by the new order or cancellation processing logic. Limit, you can attach up to 10 message attributes to a single message. Data types, attributes can be of various data types, including string, number, and binary. Message identifiers. Knowing your message. When interacting with SQS, two unique identifiers are paramount. Messaged. This is a unique identifier assigned by SQS to the message itself when it is first sent to the queue. Think of it as the message's permanent serial number. It's useful for tracking and logging purposes. Receipt handle. This is a unique identifier that SQS returns to the consumer when a message is received. It's a temporary handle that only the receiving consumer can use to delete that specific instance of the message or change its visibility. Crucially, if a message is received multiple times, e.g., due to a visibility timeout expiring, each receipt will have a different receipt handle. You must use the receipt handle from the most recent receive message call to interact with that message instance. Analogy, imagine a parcel shipment. The messaged is like the tracking number for the parcel itself. It never changes. The receipt handle is like the unique barcode on the delivery driver's scanner for this specific delivery attempt of the parcel. After delivery, that specific barcode is invalid for redelivery. Key configurable settings. When you create or configure an SQS queue, several settings directly impact how messages behave. Message retention period. This setting determines how long SQS retains a message if it's not deleted by a consumer. Default, 4 days. Range can be set from 1 minute up to 14 days. Impact. If a message remains in the queue beyond its retention period without being deleted, SQS automatically purges it. This is a safeguard against stuck messages filling up your queue indefinitely. Default visibility timeout. We've mentioned this already as a critical part of the message lifecycle. This is the default duration for which messages are hidden from other consumers after being received. Default, 30 seconds. Range can be set from 0 seconds, messages immediately visible again, making them effectively available for multiple consumers simultaneously, up to 12 hours. Impact. This value should be set based on how long your consumers typically take to process a message. If your processing consistently takes longer than the timeout, the message will become visible again, leading to potential duplicate processing. If processing is very quick, a shorter timeout might be fine. Consumers can also dynamically extend this timeout for specific messages if needed, using the Change Message Visibility API action. Delay seconds. This setting allows you to postpone the delivery of new messages to a queue. When you send a message, it won't be visible to consumers until this delay period expires. Default, 0 seconds, message immediately visible. Range can be set from 0 seconds up to 15 minutes. Impact. This is useful for scenarios where you want to allow a cool-off period before processing. For example, after an order is placed, you might delay sending a confirmation email for a few minutes to allow for immediate cancellations or modifications. This can be configured at the queue level, applying to all messages sent to it, or on a per-message basis when calling send message. SQS regions and availability. Like most OS services, SQS is regional. When you create a queue, it resides within a specific AWS region, e.g., US East 1, EU West 2. While SQS is not a global service, its regional deployment ensures high availability and durability. When a message is sent to an SQS queue, AWS automatically stores copies of that message across multiple availability zones, AZS, within that chosen region. This replication means that even if an entire AZ experiences an outage, your messages remain safe and accessible from another AZ, ensuring your applications remain resilient. Understanding these foundational concepts is the first step toward building sophisticated and reliable asynchronous systems using SQS. In the next chapter, we'll delve into the crucial distinction between SQS' two main queue types, Standard and FIFO, and how to choose the right one for your specific needs. 3. Standard versus FIFO, choosing the right queue. While all SQS queues serve the fundamental purpose of decoupling message producers from consumers, Amazon SQS offers two distinct types of queues: standard queues and FIFO, first in, first out queues. Each type is designed for different use cases, offering varying guarantees regarding message ordering and delivery. Understanding their characteristics and trade-offs is crucial for selecting the right tool for your specific application requirements. Standard queues, high throughput, best effort ordering. Standard queues are the default and most commonly used type of SQS queue. They are designed for maximum throughput and high availability. Characteristics of standard queues, high throughput. Standard queues are engineered for virtually unlimited numbers of transactions per second, TPS. This makes them ideal for handling massive volumes of messages, such as those generated by high-traffic websites, IoT devices, or large-scale data processing pipelines. At least once delivery. SQS guarantees that a message will be delivered at least once. However, under certain uncommon circumstances, e.g., during network issues, or if a message is initially delivered and then the consumer fails before deleting it, a message might be delivered more than once. This means your consumer applications must be designed to handle duplicate messages gracefully. This concept is known as idempotency. Performing an operation multiple times has the same effect as performing it once. Best effort ordering. Messages are generally delivered in the order they are sent, but strict ordering is not guaranteed. Due to the distributed nature of SQS and the way it scales, messages might occasionally be delivered out of order. For example, if you send messages A, B, C, a consumer might receive B then C. Common use cases for standard queues. Standard queues are suitable for any application where maximum throughput is a priority and where the application can tolerate occasional duplicate messages or out-of-order messages. Decoupling high-volume, non-critical tasks, sending notification emails, processing log files, image resizing, social media post-processing, where the exact order of likes doesn't usually matter. Asynchronous processing, offloading long-running tasks from a synchronous request-response flow in web applications. Buffering traffic spikes, acting as a buffer to smooth out sudden bursts of activity, allowing consumers to process messages at a more consistent rate. Example scenario. An e-commerce platform uses a standard queue to publish events for all new orders. Downstream services pick up these events to send order confirmations, update inventory, and trigger shipping processes. While receiving 2 order confirmation requests for the same order might be annoying, it's tolerable, and the system can deduplicate them. The critical aspect is processing hundreds of thousands of orders per hour. FIFO queues. Exactly once processing and strict ordering. FIFO queues are designed to ensure that messages are processed precisely once, in the exact order they are sent. The name, FIFO, actually encompasses both ordering and deduplication guarantees. Characteristics of FIFO queues. Exactly once processing. FIFO queues guarantee that messages are delivered exactly once and processed exactly once. If a producer attempts to send a duplicate message, SQS will prevent it from entering the queue if it falls within a specific deduplication interval. Similarly, SQS ensures that a consumer receives a message only once. Strict message ordering. Messages are delivered to consumers in the exact order in which they were sent. If message A is sent before message B, a consumer will always receive A before B, assuming they belong to the same message group, which we'll explain next. Throughput limitations. To maintain strict ordering and exactly once processing, FIFO queues have lower throughput limits compared to standard queues. By default, they support up to 300 messages per second, TPS, for send, receive, and delete operations. This can be increased to up to 3,000 TPS if you batch your messages. While lower than standard queues, this is still substantial for many use cases. Core concepts for FIFO queues. To enforce ordering and deduplication, FIFO queues introduce two crucial concepts: message group ID, message group ID. To enable strict ordering, every message sent to a FIFO queue must have a message group ID. Messages that belong to the same message group are always processed in order. Messages with different message group IDs can be processed independently and concurrently. Analogy: imagine a busy office with multiple queues for service. Each queue handles a specific type of customer. Within each queue, customers are processed strictly in order of arrival. However, different queues operate in parallel. In SQS, your message group ID defines which lane, or queue within a queue, a message belongs to, allowing parallel processing for messages from different groups while maintaining order within each group. Practical example. For an e-commerce system processing orders, you might use the order ID as the message group ID. This ensures that all messages related to a single order, e.g., order placed, payment processed, item shipped, are processed sequentially in the correct order for that specific order, while orders from other customers are processed concurrently. Message deduplication ID, message deduplication ID. This ensures that messages are processed exactly once. You can achieve deduplication in two ways: content-based deduplication. SQS generates the message deduplication ID by hashing the message body. If you send two identical message bodies within a 5-minute deduplication interval, SQS will treat the second one as a duplicate and only allow the first one into the queue. Provided deduplication ID. The producer explicitly provides a unique message deduplication ID when sending messages. This gives you more control and is useful if your message body might legitimately change, but the intent of the message is the same, e.g., retrying a payment, where payment attempts might have slightly different timestamps, but refer to the same logical payment request. Requirement: for a FIFO queue, either content-based deduplication must be enabled for the queue, or a message deduplication ID must be provided for every message sent. Common use cases for FIFO queues. FIFO queues are essential in scenarios where the exact order of operations and the prevention of duplicate processing are paramount. Financial transaction processing, ensuring debits and credits are applied in the correct sequence and never duplicated. Command and control sequencing, maintaining the order of commands sent to a system, such as firmware updates to devices or critical system configurations. Updating unique customer records, guaranteeing that updates to a customer's profile are applied in the exact order they occurred. Event sourcing systems, where events must be replayed in a precise order to reconstruct application state. Example scenario: a banking application uses a FIFO queue for all incoming customer funds transfer requests. Each transfer request receives a unique message group ID, perhaps tied to the transaction ID and a message deduplication ID, to prevent accidental duplicate requests from the client. This ensures that transfers are processed in the strict order they are initiated and that no transfer is ever duplicated. Trade-offs: throughput versus ordering deduplication. The choice between a standard and a FIFO queue boils down to balancing throughput, with the need for strict ordering and exactly once processing. Choose a standard queue if your application needs the highest possible throughput. Your application can handle messages being delivered more than once, i.e., your consumers are idempotent. This is typically achieved by making operations repeatable without side effects, or by using unique transaction IDs to deduplicate on your end. The order in which messages are processed is not critical, or a best effort approximation of order is sufficient. Choose a FIFO queue if you require strict message ordering. Messages must be processed in the exact order they are sent. You require exactly once processing, no duplicates are acceptable. Your application's message throughput is within the limits of FIFO queues, up to 330,000 TPS. In most common decoupling scenarios where high volume is the primary concern and systems are designed to be idempotent, a robust practice regardless, standard queues are often the preferred choice due to their superior scalability. However, for critical business processes where data integrity and sequence are non-negotiable, FIFO queues provide the necessary guarantees. By carefully considering these distinctions and understanding your application's specific requirements, you can make an informed decision and leverage the appropriate SQS queue type to build resilient and efficient distributed systems. In the next chapter, we'll delve deeper into the API actions involved in sending, receiving, and deleting messages, exploring the practical mechanics of interacting with your chosen queue type. 4. Message handling: sending, receiving, and deleting. Now that we understand the core components of SQS and the distinctions between standard and FIFO queues, it's time to get practical. This chapter focuses on the fundamental API actions that enable developers to interact with SQS queues, sending messages, receiving messages, and ultimately deleting them. We'll explore the conceptual ways these actions work and highlight critical parameters and best practices. Producing messages, sending data to the queue. The primary way for a producer to put a message onto an SQS queue is through the send message API action. Conceptual overview of send message. When your application wants to send a message, it effectively makes a request to SQS specifying queue URL, the unique address of the target SQS queue. Every SQS queue has one message body, the actual content of your message, up to 256 KB, including attributes. This can be a simple string, a JSON payload, or any other data you need to transmit. Optional parameters: delay seconds. If you want this specific message to be delayed before becoming visible to consumers, you can specify this value, up to 15 minutes. This overrides any queue-level delay seconds setting. Message attributes: a set of key-value pairs for structured metadata, as discussed in Chapter 2. For FIFO queues only, message grouped: a string identifier that dictates the message group this message belongs to. All messages with the same message grouped are processed in strict order. Message deduplication: a unique token up to 128 characters that SQS uses to identify and prevent sending duplicate messages within a 5-minute interval. This is only required if you haven't enabled content-based deduplication for the queue. What SQS returns? Upon a successful send message call, SQS will return messaged, the unique identifier SQS assigned to your message. This is useful for logging and tracking. MD of message body: an MD5 hash of the message body, which you can use for client-side verification to ensure the message was transmitted correctly. MD5 of message attributes: an MD5 hash of the message attributes. Batching messages with send message batch. Sending individual messages one by one can be inefficient for high-volume scenarios due to the overhead of making a separate network request for each message. SQS addresses this with the send message batch API action. Concept: instead of sending one message at a time, you can send up to 10 messages in a single API call to the same queue. Each message within the batch can have its own delay seconds, message attributes, etc. Benefits: reduces network overhead, which can significantly improve throughput and reduce costs, as SQS pricing is based on requests, and a batch counts as one request. Response: the response will indicate which messages in the batch were successfully sent with their messages and MD5 hashes, and which, if any, failed. This allows for partial success handling. Consuming messages, retrieving and processing. Consumers receive messages from an SQS queue using the Receive Message API action. This is a pull-based model, meaning consumers actively ask the queue for messages. Conceptual overview of Receive Message. When your consumer application is ready to process messages, it makes a request to SQS specifying queue URL, the address of the queue from which to retrieve messages. Max number of messages, the maximum number of messages to return in the single call, from 1 to 10. Visibility timeout, the duration in seconds, up to 12 hours, for which the retrieved messages should be hidden from other consumers. This is a per receive message call setting that overrides the queue's default visibility timeout if specified. It's crucial to set this to a value that gives your consumer enough time to process and delete the message. Wait time seconds for long polling. This parameter, ranging from 0 to 20 seconds, dictates how long SQS should wait for messages to become available if the queue is empty when the receive message call is made. What SQS returns? A successful receive message call returns a list of messages or an empty list if no messages are available. For each message, you get messaged, the unique ID of the message. Receipt handle, the critically important handle required to delete the message or change its visibility. Remember, this is unique to this receive attempt. Message body, the content of the message. Message attributes, any attributes attached to the message. Other metadata, MD5 of message body, MD5 of message attributes, and potentially other system attributes like senderid or approximate receive count. The critical role of visibility timeout. As explained in Chapter 2, when a message is received, it becomes invisible for the duration of the visibility timeout. This mechanism prevents different consumers from processing the exact same message at the same time, preventing duplicate work and potential data inconsistencies. Too short. If your consumer's processing time exceeds the visibility timeout, the message will become visible again, and another consumer, or the same one, might pick it up, leading to duplicate processing. Too long. If the visibility timeout is excessively long, and your consumer crashes after receiving a message, but before deleting it, that message will be unavailable for processing until the long timeout expires, potentially delaying your workload. Explicitly managing message visibility with change message visibility. Sometimes, your message processing might take longer than your initial visibility timeout or might involve multiple steps with varying durations. Instead of setting an arbitrarily long timeout, which has its own risks, you can explicitly extend the visibility of a specific message using the Change Message Visibility API action. Concept. While processing a message, your consumer can periodically call Change Message Visibility, providing the receipt handle of the message and a new visibility timeout value. This effectively resets the timer. Use case. Useful for long-running batch jobs or multi-stage processing where you want to ensure the message remains hidden while it's actively being worked on. Optimizing message retrieval. Long polling versus short polling. The receive message operation offers two polling mechanisms. Short polling, default. How it works. SQS queries only a subset of its servers for messages when a receive message request arrives. It returns immediately with whatever messages are available, even if the queue is empty. Wait time seconds equals 0. This is the default behavior if wait time seconds is not specified or set to 0. Pros, immediate response. Cons, can be inefficient. If the queue is often empty, you'll make many empty receive message calls, leading to higher costs and potentially higher latency as you persistently poll for messages. Long polling, how it works. SQS waits for messages to arrive in the queue until at least one message is available, or until the wait time seconds period expires, maximum 20 seconds. SQS queries all its servers, ensuring it doesn't miss any messages that are ready. Wait time seconds 0, activated by setting this parameter to a value between 1 and 20 seconds. Pros, reduced cost. Fewer empty receive message calls mean fewer build requests. Increased efficiency. Reduces the number of API calls to SQS. Reduced latency. Messages are available as soon as they arrive within the wait time seconds window, rather than waiting for the next short poll cycle. Cons, consumer waits for messages. Best practice, always use long polling, wait time seconds set to 20 seconds, unless you have a very specific reason not to. It generally improves the efficiency and cost-effectiveness of your SQS consumption. Deleting messages, completing the cycle. Deleting a message is a critical step because it signals to SQS that the message has been successfully processed and no longer needs to be retained. Conceptual overview of delete message. After a consumer successfully processes a message, it calls the delete message API action. This request must include queue URL, the address of the queue containing the message, receipt handle, the unique handle obtained when the message was received. You absolutely must use the receipt handle from the last receive message call that delivered this message. What SQS does. Upon receiving a valid delete message request with the correct receipt handle, SQS permanently removes the message from the queue. It is then no longer available for any consumer to retrieve. Batch deletion with delete message batch. Similar to sending messages, you can delete up to 10 messages from the same queue in a single delete message batch API call. Each entry in the batch requires its respective receipt handle. Benefits. Reduces network overhead and costs. Response indicates which deletions were successful and which failed. Common message handling pitfalls and strategies. Forgetting to delete messages, the most common pitfall. If messages are not deleted, they will become visible again after their visibility timeout expires, leading to reprocessing and potential duplicates. Ensure your consumer code always attempts to delete the message after successful processing. Implement try-catch finally blocks or similar error handling to ensure delete message is called in success scenarios. Using the wrong receipt handle. Accidentally using an old or incorrect receipt handle will result in a deletion failure. Always use the receipt handle returned from the most recent receive message call. Processing too slowly. If your visibility timeout is too short for your processing logic, messages will reappear in the queue. Either increase the visibility timeout at the queue level or dynamically with change message visibility, or speed up your message processing. Unhandled exceptions. If your consumer crashes or an unhandled exception occurs before delete message is called, the message will eventually reappear. This is where dead letter queues, covered in the next chapter, become invaluable for handling such poison pill messages. Non-idempotent consumers with standard queues. If you use standard queues, which guarantee at least once delivery, and your consumer isn't idempotent, processing the same message twice could lead to incorrect results, e.g., doubling an order, sending a notification twice. Always design consumers for standard queues to be idempotent, either by tracking processed message IDs or by performing operations that are inherently repeatable without side effects. By mastering these fundamental API actions and understanding the nuances of message visibility and polling, you lay a solid foundation for building robust and efficient asynchronous systems with Amazon SQS. Next, we will explore how SQS helps you deal with failures and problematic messages through dead letter queues. 5. Enhancing reliability, dead letter queues, DLQS. Even with careful design and robust error handling, sometimes messages cannot be successfully processed. Perhaps a downstream service is temporarily unavailable, the message content is malformed, or a critical application bug prevents its successful handling. Left unchecked, such unprocessable or poison pill messages can clog your queue, prevent new messages from being processed efficiently, and obscure underlying system issues. This is where dead letter queues, DLQS, come into play, providing a critical mechanism for enhancing the reliability and observability of your SQS-based systems. The problem of unprocessable messages. Consider a scenario where your consumer application is trying to process a message, but an external API it depends on is returning errors. Your consumer might retry a few times, but if the problem persists, what happens to that message? If the message is not deleted, it will reappear in the queue after its visibility timeout expires. This cycle repeats. The message is received, processed unsuccessfully, visibility times out, and it reappears. The message endlessly cycles through the queue, consuming compute resources from your consumers, potentially delaying the processing of valid messages, and masking the fact that something is fundamentally wrong. Such messages are often referred to as poison pills because they can poison the queue, hindering its overall performance. What is a dead letter queue and its role? A dead letter queue, DLQ, is secondary SQS queue that a source queue, your primary queue, can be configured to send messages to, specifically when they cannot be processed successfully by a consumer. Its primary role is to isolate and manage messages that fail to be processed by your consumer application. Think of a DLQ as a dedicated quarantine zone or a rejection bin for messages. Instead of letting problematic messages endlessly retry and clog your main queue, you configure your source queue to automatically move these messages to the DLQ after a certain number of failed processing attempts. Configuring a DLQ, the redrive policy. The connection between a source queue and its DLQ is established through a redrive policy. This policy defines two key parameters: dead letter target ARN. This is the Amazon resource name, ARN, of the DLQ to which messages will be sent. The DLQ is simply another SQS queue that you create, just like any other, but designated for this purpose. Max receive count. This is the most crucial parameter. It specifies the maximum number of times a message can be received and made visible before SQS automatically moves it to the DLQ. How it works: conceptual flow. A producer sends a message to the source queue. A consumer receives the message from the source queue. It tries to process it, but fails, e.g., due to an error or the application crashes. The visibility timeout expires and the message reappears in the source queue. The message's receive count, a system attribute tracked by SQS, is incremented. This cycle continues. Each time the message is received and processed unsuccessfully, i.e., not deleted, its receive count increments. When the receive count for a message equals or exceeds the max receive count specified in the redrive policy, SQS automatically moves that message from the source queue to the designated DLQ. Key considerations for max receive count. Choosing the right max receive count is important. A low count, e.g., 1 or 2, might send messages to the DLQ too quickly, even for transient issues. A high count might excessively retry messages that are fundamentally problematic, wasting resources. A common practice is to set max receive count to a value between 3 and 10, allowing for a few transient failures before moving the message. Monitoring DLQs using AWS CloudWatch. The purpose of a DLQ isn't just to hide problems, it's to highlight them. Messages accumulating in a DLQ are a strong indicator of issues in your consumer applications, upstream systems, or malformed data. Therefore, continuous monitoring of your DLQs is essential. AWS CloudWatch provides metrics for SQS queues, including specific metrics for DLQs. Approximate number of messages visible. For your DLQ, this metric tells you how many messages are currently in your DLQ waiting to be processed inspected. A rising trend here is a red flag. Number of messages sent. For your DLQ, this tells you how many messages have arrived in the DLQ. Spikes indicate problems. Setting up alarms, you should configure CloudWatch alarms on your DLQs to notify you immediately when messages appear there. For example, an alarm could trigger when approximate number of messages visible on your DLQ is greater than 0 for a sustained period, or when number of messages sent on your DLQ increases rapidly. These alerts can be sent to email, SMS, Slack, or other notification channels. Strategies for reprocessing or archiving DLQ messages. Once messages land in a DLQ, they require human intervention or a dedicated process for resolution. Common strategies include manual inspection and reprocessing. Process. Developers or operations teams can inspect the messages in the DLQ to understand why they failed. The AWS Management Console allows you to view message details. Reprocessing. After identifying and fixing the underlying issue, e.g., deploying bug fixes to the consumer, restarting a downstream service, messages can be manually moved back from the DLQ to the original source queue using the redrive dead letter queue feature in the SQS console or via the Start Message Redrive API action. This allows the patched consumer to attempt processing again. Automated retries with caution. For certain types of errors, You might have an automated process that periodically redrives messages from the DL queue to the source queue after a cool-off period. This should be used cautiously and only for specific, known transient issues to avoid an endless loop of reprocessing fundamentally broken messages. Archiving for later analysis. If messages cannot be reprocessed or are deemed unrecoverable, they can be processed by a dedicated consumer that simply archives them to an S3 bucket or a database for later auditing, analysis, or manual reconciliation. This prevents the DL queue from growing indefinitely. Best practices for DL queue management. Integrate DL queues from day one. Don't wait for problems to emerge. Configure DL queues for all your critical SQS queues from the beginning. Monitor aggressively. Treat messages in a DL queue as critical alerts. An increasing message count in a DL queue is a clear indicator that your system is not operating as expected. Clear policies. Define clear operational procedures for handling messages in. Who is responsible for inspecting them? What are the escalation paths? How are they reprocessed or archived? Analyze failure patterns. Messages in the DL queue provide valuable insights into application bugs, integration issues, and data quality problems. Regularly analyze the reasons for message failures to address root causes. DLQS are not retries. While they facilitate retries, DLQS' primary purpose is to isolate unprocessable messages. They are not a general-purpose retry mechanism for transient errors. That logic should reside within your consumer code or be handled by other AWS services like SQS receive count, combined with judicious visibility timeout values. By effectively utilizing dead letter queues, you transform what could be silent system failures into actionable insights, significantly enhancing the reliability, resilience, and operational observability of your distributed applications built on Amazon SQS. Having secured your message flow for robustness, the next step is to explore how SQS integrates with other crucial AWS services to form comprehensive, event-driven architectures. 6. SQS integration patterns, bridging services. Amazon SQS rarely works in isolation. Its true power is unleashed when it acts as the glue, bridge, or buffer between various services, especially within the AWS ecosystem. Understanding common integration patterns allows developers to build sophisticated, scalable, and resilient architectures. This chapter explores how SQS connects with other key AWS services and common architectural patterns. SQS with AWS Lambda, building event-driven architectures. Oz Lambda, a serverless compute service, is one of SQS' most powerful and common integration partners. Lambda functions can be configured to automatically process messages from an SQS queue, forming the backbone of highly scalable, event-driven, and serverless applications. How it works. You configure an SQS queue as an event source for a Lambda function. When messages are added to the SQS queue, Lambda automatically polls the queue, retrieves a batch of messages, and invokes your Lambda function with those messages as input. Benefits: automatic scaling. Lambda scales automatically to match the load on your SQS queue. As message volume increases, Lambda creates more concurrent invocations of your function. As it decreases, Lambda scales down, meaning you only pay for compute when messages are being processed. Cost-effective. Pay for Lambda only when it processes messages. You don't need to provision or manage any servers. Reduced operational overhead. No servers to manage for either your queue or your processing logic. Built-in error handling. If a Lambda invocation fails due to an error in your code, Lambda can be configured to return the message to the SQS queue, allowing for retries based on your source queue's visibility timeout and redrive policy. Use cases: asynchronous processing, offloading complex or time-consuming tasks from web requests, e.g., image resizing, video transcoding, data validation, email sending. Fan-out. A single event from one service can trigger multiple Lambda functions, each processing a message from a shared SQS queue for different purposes, e.g., an order-placed message could trigger a Lambda for inventory updates, another for shipping, and another for customer notifications. Buffering for burst loads. SQS can buffer messages from a system experiencing high, spiky traffic, allowing Lambda to process them at its own pace without overwhelming the downstream services. SQS with Amazon SNS. Combining PubSub with durable queues. Amazon Simple Notification Service, SNS, is a fully managed PubSub, publish-subscribe, messaging service. While SNS handles message delivery to multiple subscribers, it doesn't guarantee message durability if a subscriber isn't available or fails to process a message. This is where SQS integration shines. How it works. You can configure an SQS queue as a subscriber to an SNS topic. When a message is published to the SNS topic, a copy of that message is delivered to the subscribed SQS queue. Benefits: durability and reliability for subscriptions. If a consumer of messages published to an SNS topic is temporarily unavailable, messages destined for that consumer are reliably stored in the SQS queue until the consumer is ready to process them. This combines the fan-out capability of SNS with the durability of SQS. Decoupling publishers from subscribers. Publishers only need to know about the SNS topic. Subscribers can be added or removed without changing the publisher's code. Filtering. SNS allows you to apply filtering policies to SQS subscriptions. This means that an SQS queue will only receive messages from the SNS topic that match specific criteria defined by the filtering policy. This is incredibly powerful for routing messages to specific processing pipelines. Use cases: distributing events to multiple consumers. An order-placed event published to an SNS topic can be routed to multiple SQS queues, each serving a different microservice, e.g., one for order fulfillment, one for analytics, one for payment processing. Asynchronous notifications. A system can publish notifications to an SNS topic, and an SQS queue ensures that all intended recipients, or services, eventually receive it, even if they are temporarily offline. SQS for batch processing with EC2 or container services. While Lambda is excellent for event-driven, serverless compute, sometimes you need more control over compute resources or have long-running, batch-oriented workloads that are better suited for EC2 instances, ECS, Elastic Container Service, Containers, or EKS, Elastic Kubernetes Service, pods. How it works: messages, e.g., work items, file paths, are placed into an SQS queue. An EC2 instance or a containerized application continuously polls the SQS queue using receive message. When messages are received, the compute instance processes the batch of work items. Upon successful completion, the instance calls delete message for the processed items. Instances can be scaled up or down based on queue depth, number of visible messages. Benefits: pull-based work distribution. SQS acts as a central work dispatcher. Scalability. You can easily adjust the number of consumers, EC2 instances, or containers based on the volume of messages in the queue. Auto-scaling groups can even be configured to scale based on SQS queue metrics. Fault tolerance. If a compute instance fails, messages are returned to the queue after the visibility timeout and can be picked up by another instance. Use cases: data processing pipelines, processing large datasets, transforming files, or performing complex computations where results don't need to be immediate. Job queues, distributing independent tasks across a fleet of workers, e.g., video rendering, scientific simulations, large report generation. Image-video processing, queuing tasks for resizing, watermarking, or reformatting media content. Other notable integrations. SQS role as a fundamental messaging backbone makes it highly versatile. Here are a few other areas of integration. SQS as an event source for other services. Beyond Lambda, SQS can trigger other AWS services. For example, AWS step functions can consume messages from SQS, allowing you to define complex workflows that start based on message arrival. Application integration. SQS can be integrated with applications running outside of Oz, whether on-premises or in other cloud environments, using the Oz SDKs. This allows hybrid cloud architectures to leverage SQS for reliable messaging. With Amazon CloudWatch Event/EventBridge, now EventBridge. While EventBridge focuses on routing events between services, SQS can still act as a durable target for events. For instance, An event bridge rule might send specific events to an SQS queue for durable storage and later processing by a dedicated consumer. Common architectural patterns using SQS. SQS enables powerful architectural patterns fundamental to modern distributed systems. Work queue/task queue. This is the most direct and common pattern. Producers add work items to a queue, and multiple consumers pull and process these items, enabling parallel processing and load distribution. E.g., processing order fulfillment requests. Asynchronous request response, typically seen in web services. A client makes a request to a service that initially responds quickly, placing the long-running task into an SQS queue. A separate worker picks up the message, performs the task, and then, optionally, places a response message into another SQS queue that the original client monitors or retrieves results from. Fan-out. A message published to an SNS topic can be fanned out to multiple SQS queues, each serving a different microservice or processing flow. This allows a single event to trigger multiple independent actions. Buffering and debouncing. SQS can act as a buffer for bursty traffic, smoothing out spikes and preventing downstream systems from being overwhelmed. It can also be used to debounce events, collecting multiple rapid events, e.g., user clicks, into a single aggregated message for more efficient processing. Event sourcing, SQS a component. While not purely an event sourcing solution, SQS can be used to reliably transmit events in an event-sourced system, especially when combined with FIFO queues for strict ordering guarantees. By strategically integrating SQS with other AWS services, developers can build highly scalable, resilient, and cost-effective distributed systems that respond dynamically to diverse workloads. With the technical building blocks and common integration patterns now covered, the next crucial step is to secure your SQS queues and the messages flowing through them. 7. Security and access control for SQS. In any cloud environment, security is paramount. Your SQS queues can hold sensitive information, and unauthorized access could lead to data breaches, service disruptions, or manipulation of your application logic. This chapter delves into the fundamental security principles for protecting your SQS resources, focusing on identity and access management, encryption, and network control. Fundamental security principles for cloud services. Before diving into SQS specifics, it's essential to grasp general cloud security best practices, often encapsulated by a shared responsibility model. AWS responsibility, security of the cloud. AWS is responsible for protecting the infrastructure that runs all of the services offered in the AWS cloud. This infrastructure includes the hardware, software, networking, and facilities that run AWS services. For SQS, this means AWS secures the underlying servers, data centers, and the SQS service itself. Your responsibility, security in the cloud. You are responsible for protecting your data and configurations within the AWS services you use. For SQS, this includes managing access permissions to your queues, encrypting messages, and ensuring your applications are secure. The principle of least privilege is paramount. Grant only the permissions necessary to perform a task. Avoid giving broad permissions if more granular ones will suffice. Identity and Access Management, IAM for SQS. AWS Identity and Access Management, IAM, is the service you use to securely control access to AWS resources. IAM allows you to specify who can access your SQS queues and what actions they can perform. This is done through IAM policies, which are JSON documents that define permissions. When a user or application attempts to interact with an SQS queue, AWS evaluates the IAM policies attached to that user, or the role assumed by the application, to determine if the requested action is allowed. Key IAM actions for SQS. Some common SQS actions you'll want to permit or deny in IAM policies include SQS send message, allows sending messages to a queue. SQS receive message, allows receiving messages from a queue. SQS delete message, allows deleting messages from a queue. SQS get queue attributes, allows retrieving metadata about a queue. SQS list queues, allows listing all queues in an account. SQS, purge queue, allows deleting all messages in a queue use with extreme caution. SQS, set queue attributes, allows modifying queue configurations. SQS, change message visibility, allows changing the visibility timeout of a message. Example IAM policy snippet. Version 2012 to 10 to 17. Statement. Effect, allow. Action, SQS send message. Resource, ARN Oz, SQS, ACEAST 123,456,789,012, my orders queue. Effect, allow. Action, SQS receive message. SQS delete message. SQS get queue attributes. Resource, ARN Oz, SQS, ACEAST 123,456,789,012, my processing queue. Note, this is a conceptual representation of how actions and resources are specified in a policy. It would not be presented as a direct code block in the audio version. In an audio context, this would be described as: the policy would state that a user is allowed to perform the send message action on a queue identified by its Amazon resource name, or ARN, like ARN, Oz, SQS, ACEAST 123,456,789,012, my orders queue. Similarly, it would grant permission for receive message, delete message, and get queue attributes on a different processing queue identified by its own ARN. You attach these IAM policies to IAM users, IAM groups, or IAM roles. For applications running on Oz services like EC2 or Lambda, it is best practice to associate an IAM role with the compute resource, which then grants the application temporary credentials to access SQS. Queue policies, advanced access control. In addition to IAM policies attached to users' roles, SQS queues also support queue policies. These are JSON-based access policies directly attached to the queue itself. Queue policies are often used for cross-account access, allowing principals, users, roles, other Oz accounts in a different AWS account to access your queue. This is common in multi-account AWS environments. Specific action permissions, granting specific permissions based on conditions, such as allowing messages only from a particular IP address range or an AWS service principal, e.g., allowing an SNS topic to publish messages to your SQS queue. Resource-based policies. They specify who can access this specific resource, the queue, whereas IAM user role policies specify what this user role can access. Both are evaluated during an access request. Example queue policy, use case, SNS to SQS. A very common use case for a queue policy is to allow an Amazon SNS topic to send messages to an SQS queue. The SQS queues policy must explicitly allow the SNS principal sns.amazonos.com to perform the SQS send message action conditionally based on the source ARN of the SNS topic. Principal service sns.amazonos.com would be used to grant permission to the SNS service itself. Condition, ARN-like, Oz, source ARN, ARN Oz, SNS, region, account ID topic name, would further refine this to only allow messages from a specific SNS topic. This kind of policy would be described as: a queue policy often says something like, this queue will allow the Amazon SNS service to send messages, but only if those messages originated from a specific SNS topic, identified by its ARN. Encryption at rest and in transit. Protecting your messages from unauthorized access also involves encryption. Encryption at rest, server-side encryption for SQS, SSE-SQS. Purpose: ensures that your messages are encrypted when they are stored in SQS queues. Mechanism: SQS integrates with AWS Key Management Service, KMS. When you enable SSE for your queue, SQS encrypts your messages using KMS encryption keys before writing them to disk. When a consumer requests messages, SQS decrypts them before delivering them. Benefits: provides an additional layer of data protection against unauthorized access to the underlying storage infrastructure. You can use AWS managed keys, simpler, or customer managed keys, more control over key lifecycle. Recommendation: Enable SSE for any queue that contains sensitive or confidential information. Encryption in transit, SSL/TLS. Purpose: protects your messages as they move between your applications and the SQS service over the network. Mechanism: all communication with SQS API endpoints, e.g., sqs.us-east-1.amazonos.com, occurs over HTTPS, which uses SSL/TLS encryption. This ensures data privacy and integrity during transmission. Automatic: this is generally handled automatically by AWS SDKs and the AWS CLI, provided you are connecting to the correct SQS endpoints. Network access control, public endpoints versus VPC endpoints. How your applications connect to SQS also has security implications. Public endpoints default. Mechanism: by default, SQS queues are accessible over the public internet, though secured by IAM and queue policies. Your applications communicate with SQS through AWS public SQS endpoint. Considerations: while secure, traffic necessarily traverses the internet. For applications requiring the highest level of network isolation or that cannot have internet egress, this might not be sufficient. VPC endpoints for SQS. Mechanism: you can create an interface VPC endpoint for SQS within your Amazon Virtual Private Cloud, VPC. This creates a private connection from your VPC to SQS, ensuring that traffic between your applications in the VPC and SQS remains entirely within the AWS network. It does not traverse the public internet. Benefits: enhanced security. All traffic stays within the AWS network, reducing exposure to internet-based threats. Simplified network architecture. No need for an internet gateway, NAT gateway, or VPN connection for SQS access from your VPC. Fine-grained control. You can attach endpoint policies to VPC endpoints to further restrict which SQS queues can be accessed through that endpoint. Use cases: highly sensitive applications, environments with strict compliance requirements, or applications deployed in private subnets without public internet access. Implementing these security measures provides a robust defense for your SQS infrastructure. By carefully configuring IAM policies, leveraging queue policies for advanced scenarios, enabling encryption, and choosing appropriate network access methods, you can ensure that your message queues are protected from unauthorized access and your sensitive data remains secure. With the foundational knowledge of SQS operation and its security mechanisms now established, we can move on to understanding how to monitor its performance, troubleshoot issues, and optimize its cost. 8. Monitoring, troubleshooting, and cost optimization. Building robust systems with SQS isn't just about sending and receiving messages. It's also about ensuring they run efficiently, identifying and resolving issues quickly, and managing costs effectively. This chapter focuses on the vital aspects of monitoring your SQS queues, troubleshooting common problems, and optimizing your SQS spending. Key SQS metrics available through Amazon CloudWatch. Amazon CloudWatch is AWS monitoring and observability service. SQS automatically publishes a variety of metrics to CloudWatch, providing insights into the health and performance of your queues. Regularly reviewing these metrics is crucial for proactive management. Here are some of the most important SQS metrics you should monitor. Number of messages visible. The number of messages currently available for retrieval from the queue. A rapidly growing number here could indicate consumers are falling behind or have stopped processing. Number of messages not visible. The number of messages that have been received by consumers but not yet deleted, i.e., they are in flight, hidden by the visibility timeout. A high value for a sustained period could indicate slow processing or stuck messages. Number of messages delayed. The number of messages that have been sent to the queue with a delay seconds value and are not yet visible for consumption. Approximate number of messages visible. Similar to number of messages visible, but updated more frequently, approximately every 5 minutes rather than every 1 minute. Useful for getting an up-to-date view of queue depth. Approximate number of messages not visible. Similar to number of messages not visible, also updated more frequently. Approximate number of messages delayed. Similar to number of messages delayed, also updated more frequently. Sent message size, the average size of messages sent to the queue, useful for cost analysis as message size impacts pricing. Number of messages sent, the total number of messages added to the queue. Good for tracking incoming message rate. Number of messages received, the total number of messages returned by receive message calls. Note that this counts each time a message is received, so a single message appearing multiple times due to a visibility timeout will be counted each time. Number of messages deleted, the total number of messages deleted from the queue. This should ideally correspond to number of messages received over time. A significant difference could indicate processing issues. Oldest message age, the approximate age of the oldest message in the queue. A constantly increasing or very high value signifies that messages are sitting unprocessed for too long, indicating a potential bottleneck or consumer failure. This is one of the most critical metrics for identifying sluggish systems. Setting up CloudWatch alarms and notifications. Monitoring dashboards are helpful, but proactive alerts are essential. You should set up CloudWatch alarms to notify you when key SQS metrics breach predefined thresholds. Common alarm scenarios. Oldest message age is high. Alarm if oldest message age exceeds a certain threshold, e.g., 5 minutes, 1 hour, depending on your latency requirements. This is a strong indicator of consumer issues or insufficient consumer capacity. Approximate number of messages visible is high. Alarm if the queue depth remains high for an extended period. This suggests a backlog is building up. Number of messages deleted is low compared to number of messages sent. A significant discrepancy indicates messages are not being processed and deleted at the rate they are being sent. Messages in a dead letter queue, DLQ. As discussed in Chapter 5, always set an alarm on approximate number of messages visible for your DLQs to alert you immediately if any messages land there. Rate limits approaching, advanced. For high-throughput applications, you might monitor your throttled receives or throttled sends metrics, though less common with SQS due to its elastic scaling. When an alarm triggers, CloudWatch can send notifications via Amazon SNS to various endpoints like email, SMS, Slack, or orchestrate actions via AWS Lambda. Troubleshooting common SQS issues. Even with monitoring, problems can arise. Here are some common SQS issues and how to approach troubleshooting. Messages not appearing in the queue, producer side. Check producer logs. Are send message calls returning errors? Look for network issues, permission denied errors, or invalid queue URLs. Verify queue URL. Ensure the producer is sending to the correct SQS queue URL. Check delay seconds. Has the message been sent with a delay seconds parameter that is still in effect? Check number of messages delayed metric. Permissions. Does the IAM role user of the producer have SQS, send message permission on the target queue? Network connectivity. Is the producer able to reach the SQS API endpoint, public or VPC endpoint? Messages not being processed deleted, consumer side. High oldest message age or approximate number of messages visible. This is the primary symptom. Check consumer application logs. Look for errors, exceptions, or crashes. Is the consumer actually calling receive message? Sufficient consumer capacity. Do you have enough consumer instances running? Are they CPU memory bound? Worker idling? Are consumers getting messages, processing them, and then simply stopping? Visibility timeout issues. Too short. If processing exceeds visibility timeout, messages become visible again, leading to reprocessing. Check if number of messages received is much higher than number of messages deleted. Verify delete message call. Is the consumer successfully calling delete message after processing? Is it using the correct receipt handle? Check consumer code paths related to try-catch finally blocks. Permissions. Does the consumer have SQS, receive message and SQS, delete message permissions on the queue? Network connectivity. Can the consumer reach the SQS API endpoint? Dead letter queue. Are messages being moved to the DLQ? If so, investigate the reasons why they are hitting the max receive count, Chapter 5. Unexpected message duplicates or out-of-order delivery. Standard queue. For standard queues, duplicates are expected due to the at least once delivery. Ensure your consumers are idempotent. Out-of-order delivery is also possible. FIFO queue. If you're experiencing duplicates or out-of-order issues with a FIFO queue, this is highly unusual and indicates a misconfiguration or application bug. Ordering, are you using message group ID correctly? Messages with different message group ID values will be processed concurrently. Only messages within the same message group ID are strictly ordered. Deduplication. Are you providing a unique message deduplication ID for distinct messages, or is content-based deduplication enabled? Check the 5-minute deduplication interval. Are you accidentally sending the same message deduplication ID for two different logical messages? Understanding the SQS pricing model. SQS pricing is straightforward and based primarily on two factors. Number of requests. You pay for the total number of operations, API calls made to SQS. This includes send message, receive message, delete message, and other actions. Each 64 KB chunk of data in a message, body plus attributes, counts as one request, so a 200 KB message counts as 4 requests. Data transfer. Data transferred out of SQS to other AWS regions or to the internet. Transfers within the same AWS region are typically free. Example: sending one message of 70 KB in size would count as 2 requests, one for the first 64 KB, one for the remaining 6 KB. Receiving it would also count as 2 requests. Strategic approaches to cost optimization. 1. Leverage long polling. Reiterate from Chapter 4. Always use wait time seconds of 20 seconds, receive message API, for your consumers. This significantly reduces the number of receive message calls your consumers make when the queue is often empty, directly reducing request costs. 2. Batch send and delete operations. Use send message batch and delete message batch whenever possible. Sending, deleting up to 10 messages in one API call counts as a single request, plus charges for message size chunks. This drastically reduces the number of billable requests compared to single message operations. 3. Optimize message size. Keep message bodies and attributes as concise as possible. Since SQS bills per 64 KB chunk, reducing message size can lower your request count and overall costs. For very large data, use SQS to send a pointer, e.g., an S3 object key, rather than the data itself. 4. Fine-tune message retention period. Set the message retention period, default 4 days, to the minimum duration necessary for your application. If messages are processed and deleted quickly, a shorter retention period, e.g., 1 day, can marginally reduce storage costs, though this is usually a very small component of the bill compared to requests. 5. Adjust visibility timeout strategically. While not directly a cost optimizer, an efficiently set visibility timeout prevents unnecessary reprocessing of messages, number of messages received, which can indirectly impact cost by making your consumers more efficient. Avoid excessively long timeouts if not needed. 6. Monitor and alarm. Use CloudWatch to monitor your costs and usage patterns. Unexpected spikes in number of messages sent or number of messages received can indicate a runaway process or misconfigured application. Setting billing alarms can alert you to abnormal spending. By adopting these monitoring, troubleshooting, and optimization strategies, you can ensure your SQS-based systems are not only resilient and high-performing, but also cost-efficient, contributing to the overall health of your cloud operations. In the next chapter, we'll explore more advanced SQS scenarios and dive deeper into best practices for building truly robust and scalable applications. 9. Advanced SQS scenarios and best practices. Having covered the fundamentals, integrations, security, and operational aspects of SQS, we can now delve into more advanced scenarios and best practices that elevate your SQS implementations from functional to truly robust and high-performing. Handling messages larger than 256 KB. The SQS Extended Client Library with S3. One of the limitations of SQS is its maximum message size of 256 KB. While this is sufficient for many scenarios, as messages typically carry structured metadata or small payloads, some applications might generate larger messages. Trying to send a message exceeding this limit will result in an error. The solution is not to force a larger message into SQS, but rather to use SQS as a pointer to the actual large data. Oz provides an officially supported approach for this. The Amazon SQS extended client library for Java and similar patterns for other languages. How it works, conceptual. Producer. Instead of putting the large message directly into SQS, the producer first uploads the large payload to an Amazon S3 bucket. The producer then creates a small SQS message that only contains a pointer to the S3 object, e.g., the S3 bucket name and object key, or a pre-signed URL. This small pointer message, which is well within the 256 KB SQS limit, is sent to the SQS queue. Consumer. The consumer receives the SQS message containing the S3 pointer. It then uses this pointer to download the actual large payload from S3. After processing the large payload, the consumer deletes the SQS message. Optionally, it can also delete the S3 object if the payload is no longer needed. Benefits: overcomes message size limit, allows you to handle virtually unlimited message sizes. Cost-effective. S3 storage is significantly cheaper than storing large payloads directly in SQS messages, which also count towards billable request units. Best practice. This pattern is the recommended approach for large messages, as it leverages the right tool for the job, S3 for object storage, SQS for reliable messaging. Designing and implementing idempotent consumers. Crucial for robustness. As discussed, standard SQS queues offer, at least once, delivery, meaning a message might be delivered and processed more than once. Even with FIFO queues and their exactly once processing guarantee, an application-level failure might cause a message to be re-received if the consumer crashes before it can delete the message from the queue. An idempotent operation is one that, when executed multiple times with the same input, produces the same result as executing it once. Designing idempotent consumers is fundamental for building reliable distributed systems. Why it's crucial: without idempotency, receiving the same message twice could lead to duplicate orders being placed, incorrect financial transactions, e.g., charging a customer twice, excessive notifications or emails, corrupted data or inconsistent states in your database. Strategies for idempotency. Unique request transaction ID. Include a unique identifier, e.g., a UUID, an order ID, a payment transaction ID in your message body. When your consumer processes the message, check if this ID has already been processed, e.g., by looking it up in a database table or a dedicated processed IDS cache. If it has, simply acknowledge success and skip processing. If not, process the message and record the ID as processed. Database constraints. Use unique constraints in your database, e.g., on an order ID column, to prevent duplicate insertions. If an attempt to insert a duplicate record fails, you know the operation has already been performed. State management. If an operation updates a record, ensure the update is based on the current state and only applies increments-decrements once or uses optimistic locking. Transaction-based processing. For complex operations, ensure all steps are wrapped in a transaction, and the success of the transaction, and thus the message deletion, is atomic. Managing concurrency and scaling consumer applications effectively. The ability to scale consumers independently is a major SQS benefit. However, managing this scaling effectively requires careful consideration. Horizontal scaling. The primary way to scale SQS consumers is to add more instances of your consumer application. Polling strategy. Long polling. As discussed, always use long polling for efficiency. Concurrent pollers. Your consumer application can run multiple threads or processes, each making concurrent receive message calls. This allows a single consumer instance to process multiple messages in parallel. Throttling and backpressure. Ensure your consumers don't overwhelm downstream services. If a database or external API becomes a bottleneck, your consumers should ideally slow down processing, or your visibility timeout should allow the message to return to the queue for another attempt later. Auto-scaling groups, EC2 ECS, or concurrency settings, Lambda. EC2 ECS. Use AWS auto-scaling groups to dynamically adjust the number of consumer instances based on CloudWatch metrics from your SQS queue, e.g., approximate number of messages visible or oldest message age. This ensures you have just enough capacity to clear the queue without over-provisioning. Lambda. Lambda functions automatically scale concurrency. You can set concurrency limits on your Lambda functions to prevent them from overwhelming downstream services if they are not as scalable as Lambda itself. FIFO queue limitations. Remember, FIFO queues have throughput limits per message group. If you have many messages in the same message group and limited parallel processing for that group, you will hit this bottleneck. Design your message groupage strategically to allow sufficient parallelism, e.g., by using an ID that can allow many concurrent groups, such as a user ID rather than a single global ID. Implementing retry mechanisms. Application-level versus SQS redrive policies. Retrying failed operations is a cornerstone of resilient systems. SQS provides a basic receive count and DLQ mechanism, but robust retry strategies often involve application-level logic. SQS receive count and DLQ redrive policy, purpose, catches truly unprocessable messages. After max receive count attempts, the message goes to the DLQ. This is ideal for distinguishing transient failures, which should be retried, from permanent failures, which should be quarantined. Mechanism. SQS increments a counter. Consumer simply fails and doesn't delete. Application-level retries. Purpose. Handles transient errors, e.g., network glitches, temporary service unavailability, within the consumer's processing logic. Mechanism. Immediate retries. The consumer can retry the operation a few times itself, e.g., 2 to 3 times, with exponential backoff on transient errors. If still failing, it can then either throw an exception, letting the SQS visibility timeout handle redelivery, or explicitly change the message's visibility to delay its reappearance. Delayed retries. For more significant delays, the consumer can send the message itself to a separate retry queue that has a longer delay seconds, or use AWS step functions for more complex retry logic, before attempting to process it again in the main queue. This keeps the main queue clear of messages waiting for a long retry period. Best practice. Use application-level retries for transient errors. Use the SQS redrive policy and DLQ as a safety net for messages that consistently fail after all application-level retries have been exhausted, or for messages that are fundamentally malformed. Best practices for designing and naming SQS queues. Purpose-driven queues. Create separate queues for distinct purposes or message types, e.g., order processing queue, email notification queue, image resize queue. Don't mix too many unrelated message types in one queue unless they follow exactly the same processing logic. Clear naming conventions. Use consistent, descriptive names that indicate the queue's purpose and possibly the environment, e.g., prod order events, dev thumbnail jobs. Optimize visibility timeout. Set it to be just slightly longer than your maximum expected processing time for a single message. Use delay seconds wisely. Apply deliberate delays only when a message should not be visible to consumers immediately. Enable SSE encryption. For any sensitive data, turn on server-side encryption for your queues. Tagging. Use OS resource tags, name, environment, project, etc. for cost allocation, organization, and automation scripts. Capacity planning considerations for SQS. While SQS scales automatically, understanding its limits and your expected load helps in architectural design. Standard queue scale, effectively unlimited throughput. Focus on scaling your consumers. FIFO queue limits. Be mindful of the 300 TPS or 3000 TPS with batching limit. If you need higher throughput with ordering, consider sharding your message grouped values intelligently, distributing messages across many groups to allow for parallel processing. Message size. Always account for message size in your planning, as it impacts billing and, if using large messages, the S3 interaction pattern. Consumer scaling. Ensure your consumers can scale adequately to handle peak message volumes. Monitor oldest message age and approximate number of messages visible closely. Exploring more complex architectural patterns. SQS can be a building block for highly sophisticated patterns. Request response. While generally asynchronous, SQS can facilitate a request-response pattern. A requester sends a message to a processing queue, including a response queue, URL, or ID. The processor sends its response message to that specific response queue, which the requester then polls. Scattergather. A producer sends a message to an SQS queue. Multiple scatter consumers pick up parts of the task, processing them in parallel. Each scatter consumer then sends its partial result to a gather SQS queue. A final gather consumer collects all partial results and aggregates them into a final response. By applying these advanced concepts and embracing best practices, you can leverage SQS not just as a simple message queue, but as a critical component in building highly resilient, scalable, and complex distributed systems that meet the demands of modern cloud applications. The final chapter will summarize the journey and provide guidance on how SQS fits into the broader landscape of Oz messaging services. 10. Beyond the basics. The future of messaging and SQS in your architecture. We've journeyed through the intricacies of Amazon SQS, from its foundational role in asynchronous computing to advanced patterns, security, and operational best practices. This final chapter aims to concisely recap SQS power, help you position it against other Oz messaging and eventing services, and offer a glimpse into the future of distributed messaging within modern cloud architectures. A concise recap: SQS's power, flexibility, and key benefits. Throughout this book, we've seen how SQS stands as a cornerstone of scalable, resilient, and decoupled systems. Let's briefly restate its core strengths. Decoupling. SQS effectively separates components of your application, letting them operate independently and asynchronously. This is its most significant benefit, transforming rigid monoliths into flexible, distributed systems. Scalability. SQS is designed to handle virtually unlimited throughput without any manual intervention required from you. Message volumes can ebb and flow dramatically, and SQS scales with your needs. Reliability and durability. Messages are stored redundantly and are guaranteed to be delivered, at least once for standard, exactly once for FIFO. SQS ensures your data isn't lost, even if consumer applications or Oz infrastructure components fail. Cost-effectiveness. Its pay-as-you-go, serverless model means you only pay for what you use without needing to provision or manage any servers. This makes it highly efficient for variable workloads. Simplicity and integration. Despite its power, SQS is remarkably simple to use. It integrates seamlessly with other Oz services, particularly Lambda and SNS, enabling powerful event-driven architectures. Operational ease. As a fully managed service, SQS removes the burden of managing message queue infrastructure, allowing developers to focus on application logic. When to choose SQS versus other Oz messaging and eventing services. Oz offers a rich ecosystem of messaging and eventing services, each tailored for different use cases. Choosing the right tool for the job is crucial. Here's a brief guide on when to favor SQS and when an alternative might be more suitable. Amazon's Simple Queue Service, SQS, the workhorse queue, best for decoupling microservices and distributed systems, asynchronous task processing, buffering for spiky loads, building durable work queues, long-running batch jobs, and when you need a reliable message broker without managing servers. Guarantees: at least once delivery, standard, exactly once processing FIFO, best effort ordering, standard, strict ordering, FIFO, message durability. When to use it: most common asynchronous processing needs. Amazon's Simple Notification Service, SNS, the pub sub fanout. Best for mass notification systems, fan-out architectures where one message needs to go to many different subscribers, mobile push notifications, email, SMS delivery. Guarantees: at least once delivery to endpoint, best effort ordering. Not durable on its own for endpoints that are offline. When to use it: when you need to send a message to multiple recipients, or when you need a single message to trigger multiple, independent actions. Often used with SQS, where SQS queues act as durable subscribers to SNS topics. Amazon Kinesis, the streaming data platform. Best for real-time data streaming, ingesting and processing large streams of data records, capturing clickstream data, IoT sensor data, log aggregation, real-time analytics. Kinesis processes data at a finer granularity and in real-time order within shards. Guarantees: ordered real-time processing within a shard. When to use it? When you need to process a continuous flow of data in real time, often with multiple consumers reading the same stream from different points. Amazon MQ, the traditional message broker. Best for migrating existing applications to the cloud that rely on traditional message brokers like Apache ActiveMQ or RabbitMQ. It provides protocol compatibility, JMS, AMQP, MQTT, etc. Guarantees, depends on the broker chosen, generally includes durability and various delivery semantics. When to use it? When you need a managed, open-source compatible message broker and cannot easily re-architect existing applications to use SQS or SNS. Less cloud-native than SQS SNS Kinesis. Amazon Event Bridge, the serverless event bus. Best for building event-driven architectures by routing events from various sources, OS services, SaaS applications, custom applications, to various targets, filtering events, and creating sophisticated event workflows. Guarantees near real-time event delivery. When to use it? For application integration using events, especially when dealing with events from SaaS partners, or when you need flexible routing and filtering of events without needing a traditional queue storage mechanism. Event Bridge can also send events to SQS queues for durable storage and asynchronous processing. The synergistic power. It's important to remember these services are not mutually exclusive. Many robust architectures combine them. For example, SNS can fan out events to multiple SQS queues, and Event Bridge can send events to SQS queues for durable and asynchronous processing. The role of asynchronous patterns in modern, resilient, and scalable cloud architectures. The shift to asynchronous, event-driven architectures with services like SQS is not just a trend. It's a fundamental paradigm shift away from traditional monolithic, synchronous systems. This shift yields profound benefits: resilience. Decoupled components are less prone to cascading failures. If one service goes down, messages queue up, waiting for its recovery, preventing the entire system from collapsing. Scalability. Each component can scale independently based on its specific load, optimizing resource utilization and performance. Agility and innovation. Teams can develop, deploy, and update services independently, accelerating development cycles and fostering innovation. Cost efficiency. Paying for resources only when they are actively needed, serverless computing, significantly reduces operational costs. Observability. Properly instrumented asynchronous systems can provide clearer insights into bottlenecks and processing states. SQS is a foundational technology enabling these benefits. It's the sturdy conduit that allows messages and requests to flow reliably, even under immense pressure, making your applications more fault-tolerant and responsive. Brief outlook on future trends in distributed messaging. The landscape of distributed messaging continues to evolve. We can anticipate several trends, even deeper integration. Expect even tighter and more seamless integrations between OS messaging services and other OS products, simplifying complex architectural patterns. Smarter routing and filtering. Services like Event Bridge and SQS, with content-based filtering, will likely gain even more sophisticated capabilities for routing and filtering messages and events at scale, allowing for more granular control over data flow. Increased focus on observability of asynchronous flows. Tools and features for tracing and monitoring messages through complex, multi-service asynchronous workflows will become even more critical and sophisticated. Enhanced developer experience. OS and the broader community will continue to simplify the developer experience for building event-driven applications, making it even easier to adopt these patterns. Guidance on continuous learning and experimentation with SQS. Mastering SQS, like any cloud technology, is an ongoing journey. Read the official documentation. The AWS SQS Developer Guide is an invaluable, up-to-date resource. Refer to it for the latest features, best practices, and detailed API specifications. Experiment. The best way to learn is by doing. Set up test queues, send messages, and build example consumers. Experiment with visibility timeout, delay seconds, DLQS, and batching. Observe the metrics in CloudWatch. Explore AWS Well-Architected Framework. Understand the principles of the well-architected framework, particularly the reliability and performance efficiency pillars, as they apply directly to building robust SQS-based systems. Participate in the community. Engage with the AWS developer community through forums, blogs, Stack Overflow, and local meetups. Learn from others' experiences and share your own. Stay updated. Follow AWS news blogs, event announcements, and expert content creators to keep up with new SQS features and best practices. Amazon SQS may be simple in name, but its impact on modern data architectures is profound. By understanding and strategically applying its capabilities, you are well equipped to build the next generation of resilient, scalable, and cost-effective applications that power our increasingly asynchronous world.